Today we are going to summarize on whatever we have discussed in this course, which is on chemical and biological thermodynamics, principles to applications. Thermodynamics is a very important subject, whether it comes to chemical sciences, biological sciences, pharmaceutical sciences, and even in technology. We started this course from very simple concepts with an idea that if there are any confusions in understanding the fundamentals, that should be removed. We decided that we will follow the science and conventions recommended by IUPAC, International Union of Pure and Applied Chemistry, so that there is no confusion in various equations which are used in describing different laws. We started with the definition of system. System is the most important part of the universe because it is the system in which we are interested in. And then we went on describing the various parts of various types of the system: open system, closed system, insulated system. And it is up to the scientist or a technologist to decide how to use the properties of the system. For example, it is the properties of the system which will decide how the system will behave. And also, it is the properties of the system that a technologist will use these properties to come up with the sophisticated instrumentation. So that is why, as commented on this slide, the system was subdivided into different types of the system, and then the types of the system will decide the properties of the system, and the types of the system will also be utilized into developing technological advances which definitely depend upon the properties of the system. So therefore, system has a specific significance when it comes to thermodynamics. It is the system which will decide that how we utilize its properties. After the system, we introduced the concept of surroundings. Let us take a look at the slide. As described over here, surroundings play a very important role when there is a thermal equilibrium between system and surroundings. It is very important how we sense what is going on in the system. The observations can be made directly into the system, and observations can be made in the surroundings also. But if the observations are to be made in the surroundings, then there has to be heat exchange between system and surroundings. Let us remember the example that I took in the beginning of the lecture, that suppose if I am teaching in a classroom and the walls of the classroom or the door allows my sound to escape. That means it is a closed system. The students cannot go out, my voice can go out. Then a person who is standing outside in the corridor can listen to whatever I am teaching. And therefore, that person is a sensor. Whatever activity is going inside the system can be sensed outside. And therefore, the surroundings have a special role to play whenever there is a thermal equilibrium between system and surroundings. That means, if we are interested in very accurately determining the heat changes which are going on inside the system, it is possible to be determined in the surrounding provided there is a thermal equilibrium. Therefore, surroundings play a very important role. Then we discussed the first law of thermodynamics. All the laws of thermodynamics are based on experimental observations. And based on experimental observations, the first law was put forth, according to which the total energy is conserved. The total energy remains constant, although it can be converted from one form to another. And this was put forward in the form of a mathematical equation that whenever there is a change in internal energy, that changed internal energy is used up in doing something, either in heating up the system or by doing work on the system. And that is what is represented in this slide, that the total energy of the system is conserved, total energy is conserved. And this, any change in the internal energy is the total energy of the system added up in all the forms. The change in internal energy can be used up either in heat or by doing work, and that was the first law of thermodynamics. And after that, we went on discussing the second and third law of thermodynamics. Second and third law of thermodynamics have a special significance, because second law, which introduces the entropy, is connected with the spontaneity of a process. Remember, we took an example of throwing a ball on the ground. If I just throw a ball on the ground after a special bounces, it comes to rest. No work needed to be done in that case, because when you just release a ball, it's a spontaneous process, no work is done. And whenever the ball was hitting the ground, it was generating thermal motion into infinite atoms of the floor. And there we connected this spontaneity in the direction of generation of more disorder. And therefore, this disorder is connected to entropy. That is why the changes in entropy play a significant role in deciding whether a given process will be spontaneous or not. Let us take a look at the slide. In the second law, we introduced the concept of entropy and connected the spontaneity of a process in the direction of generating more disorder. We further went on discussing the criteria of spontaneity. Criteria of spontaneity is very important, because we should know under what conditions a process will be spontaneous. We discussed that if you want to apply second law of thermodynamics in deciding whether a process will be spontaneous or not, we needed to calculate the entropy change in the system, entropy change in the surrounding, add up the both, and if the total turns out to be positive, then the process is spontaneous in that direction. That is why the second law states that the total entropy change in an isolated system always increases during a spontaneous process. We then further discuss that you can have the criteria of spontaneity in terms of the change in properties of the system alone. And then based on the Clausius inequality, we derived several criteria of spontaneity which were in terms of the changes in the properties of the system alone. Some of those criteria were a little tedious to obtain, because maintaining, for example, maintaining the entropy of a system constant is not that easy. But certain criteria of spontaneity, for example, dg at constant temperature and pressure less than equal to 0 for a spontaneous process was very important, because maintaining the temperature and pressure of the system is easy. And this criteria of spontaneity is widely used. Whenever we say that the process will be spontaneous when the change in Gibbs energy at constant temperature and pressure is negative. And we also use the criteria of change in Gibbs energy at constant temperature and pressure equal to 0 for that of the system at equilibrium. Then let us take a look at the slide again. We further discussed the third law entropies. And this third law entropies were introduced after discussing the third law of thermodynamics. According to the third law of thermodynamics, we discuss that entropy of each element is positive, and it may become 0 at absolute 0. It does become 0 at absolute 0 in case of perfectly crystalline substances, including compounds. We also discussed that if there is a configurational disorder at absolute 0, the entropy may not be 0 at absolute 0, and this we discussed by taking an example of carbon monoxide. We further went on discussing the technological applications of the third law of thermodynamics, and we discussed that by using adiabatic demagnetization process, it is possible to obtain very low temperature of the order of picokelvin. We further went on discussing how to measure entropies, measurement of entropies. Measurement of entropies is possible by using calorimetry. We took an example of finding out or determining the entropy of a substance A in the gaseous form at any general temperature. There we discussed that we need to make measurements from absolute 0. We need to account for all the phase changes. And then we discussed that it is not possible to make measurements at absolute 0 because it is not possible to arrive at that temperature. And that brought in discussion on d by third power law. And as I discussed earlier, we did focus on the technological applications of the second and third law of thermodynamics. Then we discussed Gibbs energy G, Helmholtz energy A, and we further discussed that if we are interested in knowing the maximum work which can be drawn from a system, we have to calculate delta A. And if we are interested in knowing the maximum known pressure volume work, then we have to act upon delta G. So this delta A and delta G are very important changes in thermodynamic properties, because we are always interested in knowing how much work we can draw from a system. And if we want to talk about the total work, inclusive of pressure volume or non-pressure volume work, we must always act on A and calculate delta A. And if we are interested in calculating in knowing the non-pressure volume work, which sometimes several books describe as extra work or other work. Then we have to calculate delta G, and one such example is electrical work. So, therefore, delta A and delta G are very important changes in thermodynamic properties. We also discussed that why delta A is called the change in Helmholtz free energy. We discussed what is free in this free energy. And then we went on discussing the properties of G and A and their connection to volume and entropy. You remember that equation dG is equal to VdP minus SdT that connects the changes in J, and we also discussed the equation for dA so that the changes in G and A can be connected to other important thermodynamic properties. Then we started discussion on ideal solutions, deviations from idealities in gases and solutions. We introduced chemical potential. Chemical potential is central to chemistry when it comes to discussion on equilibrium. So, any advanced discussion in physical chemistry when it comes to equilibria should be done in terms of chemical potential. Then we started discussion on fugacity and activity. Why fugacity and activity are important to discuss? We discussed what is an ideal gas, we discussed what is an ideal solution. In an ideal gas, there are no intermolecular interactions, whereas in ideal solution, there are intermolecular interactions, because if there are no intermolecular interactions, then the solution will not be formed or two liquids will not be miscible. In an ideal solution formed by mixing liquid A and liquid B, the average AA interactions and average BB interactions are same as average AB interactions. We also know that most of the systems do not follow ideal behavior. The difference in intermolecular interactions in solutions or the intermolecular interactions in gases bring in non-ideality. And in order to account for non-ideality, in gases, fugacity was introduced. Fugacity is effective pressure or escaping tendency of the gas molecules. And then we discussed activity. Activity we discussed as effective concentration. And that brought in a discussion on the fugacity coefficient or the activity coefficient. The fugacity coefficient or activity coefficient capture the deviation or the extent of deviation from ideality. All the deviations from ideality are captured by the activity coefficient. So, therefore, whenever we are making some measurements, we must use the activities or fugacities unless the solution is so dilute and the gas is such a low pressure that the molecules can be considered very, very far apart and the activity can be equated to concentration or activity can be equated to molality or mole fraction, or fugacity can be equated to the pressure of the gas. We talked about ideal solutions, deviation from ideality, and then we started discussing partial molar properties. In fact, chemical potential itself is a partial molar property, because chemical potential is change in Gibbs energy when 1 mole of a substance is added at constant pressure and temperature, keeping the other components at same concentration. And we also discussed partial molar volume and partial molar adiabatic compressibility. For example, partial molar volume is an extremely important thermodynamic properties, is a very important thermodynamic properties if we are interested in understanding intermolecular interactions. Because volume not only depends upon the mass and density, the volume also depends how a substance interacts with other components in a mixture. For example, if we are talking about an aqueous solution, and then when we add a substance into water, how it affects the structure of water will very much decide the partial molar volume of that substance in aqueous solution. And the partial molar volume of transfer from water to mixed aqueous solution can tell us about the nature of intermolecular interactions operating in that system. And therefore, the partial molar properties play a very important role when it comes to an understanding the intermolecular interactions operating in solutions. And then we discussed heat capacity and its applications. We discussed that heat capacity is a very important connector between various thermodynamic properties from one temperature to another temperature. Not only an important connector, but also heat capacity is an indicator of the strength of a system. Because if a system is very strong, then its heat capacity will be more. And if the system is very soft, its heat capacity will be less. And therefore, this property can be used in discussing about the strength of a system. We went on discussing chemical equilibrium constant, which is very important in discussing the optimization of a process. And we further went on discussing the applications of equilibrium constant, its role in chemical and biological processes. Equilibrium constant is very important thermodynamic property, because equilibrium constant decides the yield in a reaction. It is not just a number, but it gives important information on how much the product is formed. It also gives information on how a ligand interacts with a protein and how the ligands interact in biological systems, under what conditions, and it has played an important role in rational drug design, as we discussed in several chapters. We further went on discussing biological standard states and pH. Later on, we switched over to thermodynamics in systems of biological interest, specifically with a focus on protein folding, protein ligand interactions, protein solvent interactions, and enzyme catalyzed interactions. Protein folding, which is how a primary sequence of amino acid takes up a unique three-dimensional functional form of a protein, is called the protein folding problem. We discussed how thermodynamics is important in this process and how the use of calorimetry has given important information on the forces which hold the protein, three-dimensional structure of the protein intact. We also discussed how thermodynamics is important in protein ligand interactions, protein solvent interactions, and enzyme catalyzed reactions. Let's take a look at the slide. We discussed that more than 50 years we have spent in addressing the protein folding problem, and still we do not have an answer to why a unique three-dimensional fold is obtained from a given primary sequence. Although the computational chemists claim that they can give the folding code for small peptides, but for larger proteins we do not have the protein folding code. And that is why now still there is a need for experimental evidences for the funnel model, which is used as one of the best model to describe protein folding problem. And thermodynamics plays a very significant role in this, because a minimum energy configuration is what is the final fold of a protein. At length we discussed the ultrasensitive microcalorimetry, its use in protein folding, nucleic acid melting, which is differential scanning calorimetry has played an important role in this, and ligand macromolecule or macromolecular interactions we discussed with the use of isothermal titration calorimetry. And the aim was demonstration of versatility and power of microcalorimetry in elucidating biologically important processes. We discussed the principle of differential scanning calorimetry and the applications of differential scanning calorimetry in the area of protein folding, pharmaceutical sciences, and many other areas. We also discussed isothermal titration calorimetry, its principle and its huge applications in addressing the interaction of ligands with variety of biological macromolecules. We also discussed that ITC is not just important in addressing the biological systems of interest, but even in several non-biological interactions. We discussed that obtaining thermodynamic signatures from the technique like isothermal titration calorimetry are very important, and such thermodynamic signatures can be obtained in a single experiment, which play an important role in engineering binding affinity and rational drug design. Because the thermodynamic signatures help us in identifying the various causes which help in deciding how to engineer binding affinity in a given molecule, in a given potential drug. Because delta G has to be negative when we want to achieve an affinity. We discussed how polar desolvation can be costly and how hydrogen bonds and van der Waals interaction can contribute in the negative value of delta G. And also we also talked about the desolvation, how desolvation can also contribute in negative value of delta G naught, and on the other hand structuring can also lead to some penalty. So these final discussion helped us in discussing that how to improve the functional groups in a given molecule which is already existing, on in novel synthesis of new molecules or newer molecular entities which should have a desirable effect, a desirable affinity. If our aim is having more exothermicity, then what kind of functionality should be introduced, and also that where it should be introduced so that it should not lead to enthalpic penalty if obtaining exothermicity is the major goal. We further went on discussing that if the binding is very, very tight and beyond the determination by isothermal titration calorimetry or other equilibrium methods, then differential scanning calorimetry can be used in estimating the ligand binding constant or affinity constant associated with the ligand binding of the order of 10 raised to the power 20 or higher, 10 raised to the power 20, 10 raised to the power 30, 10 raised to the power 40 or even higher. And we discussed how differential scanning calorimetry can be helpful in addressing the thermodynamics of the process from folding unfolding to ligand binding. Not only in addressing the thermodynamics of a process, we further discussed that isothermal titration calorimetry is very important in determination of the kinetics of the reaction. The rate of the reaction is connected with the enthalpy change and also the heat rate, that is the rate of flow of the heat. And from the isothermal titration calorimetric measurements, it is possible to address the kinetics of the reaction. To summarize, the significance of understanding thermodynamics of the process lies in a variety of areas. Let us take a look at some of those important areas. Chemical sciences, biological sciences, pharmaceutical sciences, chemical industry, pharmaceutical industry, and research in chemical and pharmaceutical sciences. I am sure that the concepts which were covered in this course and their connection to the applications in variety of areas will be very, very helpful, not only in explaining or in obtaining the deeper insights into the phenomena, into the process under investigation, but also in various types of industries, in various industries such as chemical industry, pharmaceutical industry, specifically when we talk about the rational drug design. As listed in this slide, that from chemical sciences to biological sciences to pharmaceutical sciences, chemical industry, pharmaceutical industry, the deeper understanding of thermodynamics will very, very be helpful in all of these areas, including research in chemical, biological, and pharmaceutical sciences. Wish you all the best, and thank you very much.